In the year that has passed, the tireless work of rovers and orbital probes has yielded unprecedented discoveries on the enigmatic planet of Mars. These findings not only shed light on the geological and climatic history of the planet, but also offer tantalizing hints of the possibility of primitive life forms in its ancient past. Since their inception, rovers such as Perseverance, Curiosity, and Zhurong have traversed the harsh and mysterious landscapes of Jezero Crater and the surrounding areas. For instance, Percy Weatherings, who has been exploring the surface of Mars for over 4 years, has made several groundbreaking discoveries. One of these discoveries is connected with the unique rock known as St. Paul's Lantern. The intriguing fragment surprises with its texture, boasting hundreds of small spherical features, some elongated and others angular. These structures suggest that the rock was formed through complex processes involving the action of liquid water and subsequent reworking of the material by meteorite impacts or rapid cooling of molten droplets. Researchers call this rock floating because its chemical and physical composition does not match the typical characteristics of local sedimentary deposits, indicating that the material was transported and redistributed by dynamic processes that occurred on Mars in the distant past. This discovery not only expands our understanding of the processes that occurred on the planet, but also raises important questions about how liquid water could have circulated beneath ancient landscapes, leaving behind such striking textural features. The tubes are waiting to be picked up by NASA's Mars Sample Return mission. Who knows, these could be eggs of alien forms. In any case, the stranger approves. In parallel, the Curiosity rover continues to contribute to the study of organic chemistry on Mars. Recent analysis of Abracep and the famous Cumberland rock revealed the presence of long organic molecules such as undecane and deticane, which are fragments of acids that are the basic building blocks of cell membranes on Earth. This discovery is of great importance, as until now it was believed that organic chemistry on Mars was limited to relatively simple compounds. The discovery of more complex molecules suggests that conditions on ancient Mars may have supported chemical processes similar to those seen in biological systems. However, the question remains open whether these molecules are the product of abiotic reactions caused by geochemical processes or whether they are the remnants of ancient microbial life. The very fact that such compounds exist encourages us to continue searching for evidence of life in the depths of ancient sediments, since it is precisely such molecules that can serve as reliable biosignatures. Equally important are the data obtained from orbiters such as Embryo and Mars Odyssey. Studying thin layers of rock revealed from orbit helps reconstruct the dynamics of processes that have occurred on the planet over billions of years. These data made it possible to determine changes in climate, the distribution of various minerals, and to identify small details that had escaped the attention of previous studies. Thus, orbital data become an indispensable tool for selecting the most promising areas for further research from the surface and for assessing the global context of objects discovered by rovers. The Chinese rover Zhurong played a special role thanks to its advanced subsurface radar, which was able to detect previously invisible structures resembling beach sediments. These data provide strong evidence that there was a huge ocean in the north of Mars, now gone, and that its coastline was extensive and had properties similar to Earth's beaches. The Chinese rover's radar was able to peer up to 80 meters below the surface, revealing layers of sediment that slope at an angle of approximately 15. This corresponds to the nature of the formation of beach sediments, where wave and tidal processes play a key role. This discovery supports the hypothesis of the presence of an ancient ocean on Mars, and also indicates that coastal zones were dynamic regions and could have served as a refuge for the emergence of the first forms of life. Just as on Earth, it was precisely these conditions that contributed to the emergence or maintenance of biological systems. All these observations from the surface and from the orbit of the planet reveal to us a whole mosaic of processes that at one time made Mars a planet with active geological life and possibly with the first signs of biological activity. In addition, the missions are aimed not only at studying the past, but also at testing new technologies that will help pave the way for future manned expeditions. Thus, the rovers continue to collect rock samples for their future return to Earth, which will be a decisive step in conducting detailed laboratory analysis using the latest methods. The resulting samples could contain valuable information about the composition of the Martian crust and the presence of traces of ancient water and organic molecules that may have survived from when Mars was warmer and wetter. In addition to geological and chemical research, modern missions also focus on studying the atmosphere and climate processes. Orbital vehicles can already track seasonal changes in the composition and density of the Martian atmosphere and assess the impact of field storms and other atmospheric phenomena. These data are vital for understanding how Mars lost most of its atmosphere and for modeling the processes that led to the planet's transition from warm and wet to cold and dry. Moreover, studying atmospheric conditions has practical implications for future missions, as understanding the dynamics of the Martian atmosphere helps in developing communication systems and ensuring the safety of manned expeditions, and new engineering solutions are tested, such as autonomous control systems, robotic instruments for collecting samples, and technologies that allow oxygen to be extracted from carbon dioxide, which is prevalent in the Martian atmosphere. These technological breakthroughs demonstrate the capabilities of modern space engineering and serve as key steps towards future human missions where life support and autonomy of spacecraft will be vital issues. It is impossible to overestimate the significance of these discoveries for space science. Taken together, the data from Perseverance, Curiosity, and the Chinese rover, as well as MRO, Odyssey, and other orbiters, form a mosaic in which every detail, from tiny organic molecules to huge structures of ancient beaches, has its own unique place. These observations allow us to reconstruct the history of the evolution of Mars, and also to think about what conditions are necessary for the emergence of life on other planets, or what they once lost, like the planet Venus once did. Modern research shows that even in the harshest conditions, biological processes can exist, and therefore the search for life beyond Earth is becoming a real task, which humanity is already approaching with scientific rigor and technological boldness. All this new data gives hope that over billions of years of evolution, the first forms of life could have emerged, leaving behind invisible but tangible traces. These scientific advances are stimulating further development of technologies for manned missions aimed at returning Martian samples and perhaps establishing a permanent human presence on the planet, or at least practical robots that could prepare everything for colonists. And we will continue to follow the Martian news. Music, 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 applause, yeah.